Hello, everyone. Welcome to Spot, the new science public online talk series brought to you by the Faculty of Science at the University of Manitoba. Today's talk is by Dr. Michael Gericke from the Department of Physics and Astronomy at UManitoba. I'll be moderating this talk today. My name is Samar Safihar. I'm the faculty's lead for Equity, Diversity, and Community. I'd like to welcome all of our online viewers to this new series. For those of you who are new, the goal of this series is to enhance our culture of shared knowledge and experience across our faculty and with our students and alumni. We wanted to better support our students and bring the community together in these difficult times and in this new environment of virtual learning and communication. Spot will feature diverse and engaging speakers alternating between our science faculty and alumni, happening on Fridays at this time throughout the summer. Special thanks to the Spot team working behind the scene and shown here, helping bring this new series to life. Thank you also to all of our speakers for providing their precious time and for making this possible and accessible to all. We do have a lineup of many interesting talks, so please make sure to sign up on the Spot website for the upcoming ones if you didn't do so already. Now, some housekeeping items first. The talks will be brief, just 15 to 20 minutes long, followed by a question-answer period. For that, you need to open another window in your browser or use another device. Go to slido.com, and the event code will be 6307. Feel free to enter your questions throughout the talk. That is, you don't have to wait till the end, and I'll be moderating and reading these questions out loud to the speaker. You could choose to enter your name or choose to remain anonymous. Now it's my pleasure to introduce our speaker, Dr. Michael Gericke. Michael received his PhD from Indiana University, followed by two postdoctoral fellowships at the Los Alamos National Lab and the Jefferson Lab in the United States before moving to the University of Manitoba in 2007. He's currently full professor in physics and astronomy, and he also acts as vice chair for the Canadian Association of Physicists, the Division of Nuclear Physics. Dr. Gericke is passionate about fundamental physics and is an expert in building instruments to answer some of the most fundamental questions in nature. His research is more specifically in the area of nuclear and particle physics, and he has expertise in the development of novel particle detectors. His research makes use of high-precision detectors to search for new physics beyond the so-called standard model. He has unique expertise in not only the development of these particle detectors, but also the associated simulations, data acquisition, analysis, and modeling. He's currently leading and heavily involved in new experiments at the forefront of the field. What I personally find most fascinating about his work, being an astrophysicist myself, is that the work he does at the very small scale, subatomic scales, has implications on our understanding of the matter and forces governing our own universe. So, Michael, the spotlight is on you now.
Okay, thank you, Samar. Thank you very much for the invitation to give this talk here. I'm looking very forward to being able to tell you about my research, and I'm hoping that I can make this broadly understandable by trying to stay away from too many technical details about the work. So this will be a pretty broad overview over what types of detectors we use and for what purpose we use them. Most things to us are actually invisible. Most things in the universe, most things that exist to the naked human eye or to the human senses are not detectable. So what you see here on the slide is what's generally referred to the electromagnetic spectrum. And there is a very small region at the center there that's that we call the visible spectrum. But in reality, the spectrum is a lot broader than that, extending in wavelength from the very large scale to the millions of meters, all the way down to the very small scale, sort of at the 10 to the minus 18 meters, all the way down to 10 to the minus 21, which is where current high energy particle physics experiments are doing their research, exploring the very small scale structure of life, or of, I should say, of nature and matter. So there is, for example, the very large array, for example, which is a radio astronomy array in New Mexico, which looks at the very long wavelength limit of the spectrum. And then at the very other end, for astrophysical phenomena is, for example, HESS. There are other examples, but this is the one I picked, that does X-ray and gamma ray observation. In between, of course, there are a lot of other instruments, including, for example, electron microscopes and just standard microscopes. But you don't just have to use light or the electromagnetic spectrum itself. You can use particles to investigate the structure of matter, life in general. So here are some examples that I've picked of experiments that do this with particles and with light. So, for example, at the very long wavelength limit, here you have ultra cold neutrons. So the long wavelength here, or the low energy, refers to the particles that we consider to be the probes. So here you have what are called ultra cold neutrons. They're very, very slow neutrons. And this is being done at TRIUMPH out in Vancouver. Then you have, for example, cold atoms, or cooled and trapped atoms. That's also done at TRIUMPH. And then as you go to higher energy, again, where you look more at life science, using the Canadian light source, for example, then you can build particle physics experiment, which is my field over here. There's one called the QEEC experiment, which ran at a facility called Jefferson Lab in the United States, that was led to large part by the group at the University of Manitoba, which explores things at the sort of 10 to the minus 15 meter scale. And then you have newer experiments coming up, such as the molar experiment that I'm working on, that goes all the way down to 10 to the minus 16, even 10 to the minus 18 and further. And then you have the very large experiments, such as, for example, the experiments at CERN, at the Large Hadron Collider, that currently investigate structure of matter at the small. So usually what you want to do is you want to use your observations to investigate nature in general. But when we do this with our eyes, the information that we get, generally speaking, is very qualitative. So for example, there's color, green, blue, yellow, and so on and so forth. What we really want to measure there more precisely is energy. Then there's, for example, location, which general direction is the light coming from. What we really want to know is sort of coordinates and angles. There's, of course, the shape. Is it big, small, sharp edges, round, irregular, and so on and so forth. So we want to get some sense of the spatial patterns. Then there's intensity. In other words, how bright is it? So we measure rates in our detectors. And then there's the event itself. When did something take place and where did it take place? So this has a lot to do with timing. So energy, coordinates and angles, spatial pattern, rates, and timing is what we try to get out of detectors when we try to make precise measurements. Of course, if something is really small, we also need magnification, or if something is very far away. With long wavelengths compared to the size of the object, we can't really tell anything about the internal structure. So in order to say something about the internal structure of objects, we need to go to shorter wavelengths. And to understand something in universal terms, we really want quantitative information. So we usually want to control what we call the initial conditions. So set up samples and control the incoming light or beam of particles. And we want to implement a more precise way to measure the outcome. with customized detectors. So, for example, when we look at the very large-scale objects out in space, we can use observational astronomy or high-energy astrophysics. We don't control the initial conditions of the sources in that case, but with the high-precision detectors, we can still measure the energy of particles, the source location, the brightness, the large-scale structure and composition. But in order to really understand the underlying physics, the precise small-scale underlying physics that produce those signatures, we have to do experiments where we set up beams, for example, and then do our experiments. So what do the different wavelengths actually tell us? In general, the shorter the wavelength of the probe, the shorter the distance we can observe in the structure. Sort of below 10 nanometers, quantum effects start to set in. It starts to get harder and harder to do this with light. I mean, you could have a very high intensity beam of gamma rays to do it with, but those are hard to control and focus. It's easier to do with beams. And we know that all matter particles have a so-called matter wave associated with it, the de Broglie wavelength, which is inversely proportional to the mass of a particle and its speed. So with subatomic particles, we can extend our wavelength range to smaller and smaller wavelengths significantly by speeding them up. So the smaller the objects we want to see, the higher the required energy of the probes, photons or particles. There are some exceptions to this, which I can't really talk about. There's not enough time for me to talk about, but you can, for example, perform precision measurements that exploit certain symmetries or the lack thereof of nature. So here's an image. Again, we start at the very large wavelength where we sort of investigate large-scale structures out in space. We move to shorter wavelengths and slightly higher energies to study everyday macroscopic objects. Then just past the visible, sort of in the UV and low X-ray range, we start to look at cells and molecules, for example. By the time we want to look at individual atoms, we're down to 10 to the minus 10, so just sub-nanometer scales. In order to look at the nucleus, we have to go all the way down to 10 to the minus 14 to 10 to the minus 15 meters in order to look at a proton, for example, or a neutron. And then if we want to resolve even smaller scales, such as where quarks start to be important in describing protons and neutrons, we have to look at even shorter distance scales, sort of 10 to the minus 18 and beyond. So how do we do this? Well, in order to do this, we set up accelerators and detectors, and they're really just like big microscopes. So here, for example, is sort of schematically indicated a long accelerator. In this particular case, at Jefferson National Laboratory in the United States, they're accelerating electrons to very high speed. So here, this speed of the electron v here is almost equal to the speed of light c. And that gets you down, for those energies, down to a wavelength of roughly a femtometer, which is just about the size of a proton. So you start to resolve individual protons and you can study their interactions. Then what else you need is, of course, you need a target. So that would be your sample. If you think in terms of microscopes, you need an aperture and you need a magnet that focuses and magnifies the scattered events. And then you need something like an eye, which is our detectors. Down here at the bottom right, you have the so-called QWEEK experiment at Jefferson Lab, which was a big effort for our group here at the University of Manitoba for a long time. So what do magnets do? They steer and focus the scattered particles into the detectors. They help identify particle type because, you know, if a particle is positively charged, the magnet will steer it one way. If it's negatively charged, it will steer it another way. And it will also help in measuring the particle energy. The slower the particle in a given magnetic field, the more it will bend a charged particle. And the faster it is, the less it will bend Neutral particles, indicated here by this blue line, won't bend at all. We can use detectors to measure the origin, where the particle came from or scattered, called the vertex. We can measure the direction of particles. It's called tracking. We use detectors here in front of the magnet and after the magnet to do this. We can do particle ID in detectors located throughout the experiment to identify the type of the particle, measure the rate of the scattered particles by just counting, and we can do calorimetry, or in other words, measure the energy of the scattered particles. There are many different types of particle beams with which this is done. Two examples, for example, the very high energy proton beam at the Large Hadron Collider in CERN accelerates protons to 7 TeV, which gets you in a fixed target experiment down to 10 to the minus 19 meters. In a Jefferson lab, electrons are accelerated to 12 GeV, very close to the speed of light in both cases, which gets you down to a wavelength of about 10 to the minus 18 meters. The only other way to get even higher energies is to accelerate both particles, and this is the basis for so-called collider experiments, where you basically accelerate both the probe and the sample. And one example here is the ATLAS detector at CERN. At CERN itself, at the LHC, you get a total energy, since you both accelerate both particles, in this case, proton-proton collisions, to 13 or 14 TeV, which gets you down to 10 to the minus 21 meters. And then the other example is an electron-positron collider in Japan that gets you down to 10 to the minus 18 meters. Why do these detectors have to be so big? The primary reason for that, the two primary reasons for that, is that you want to capture all the particles. So hermeticity, in other words, complete enclosure of the interaction region, is important in this case. You don't want to miss any of the particles that come out of the reaction. Missing energy, for example, if you missed a particle and you couldn't measure its energy, would lead to incorrect event reconstruction. In other words, you couldn't tell exactly what happened during the collision. And you want to stop most particles. And if you can't stop them completely, you want to detect them. So here again is a picture of the CMS experiment at CERN. And the reason why I picked this is because it is one of the largest detectors in the world, beside the ATLAS detector. And here is a beam eyes view. So the beam, you can imagine going into the page here in the center, and here's a cross-section of the detector. And you can see various different particles, muons, electrons, charged particles, neutral particles, photons, captured in different regions of the detector, with the exception of the high-energy muons, which just leave the detector altogether, but they can be very well tracked by the detector. So the detector has to be very large in order to make. So how does particle detection actually work? It happens via energy loss in some material. So the detector, the chosen active detector material, and there are a couple of different processes that can happen. For charged particles, for example, we have ionization, the so-called Bremsstrahlung. So the first picture here on the upper right is ionization, where the electron gets removed from the atom. Then we have Bremsstrahlung, where the electron, in this case here, is a moving electron, but it can be another particle too, radiates a photon when it bends around the field of a nucleus. We have the Cherenkov process. We have nuclear interactions. For hadrons, like protons, for example. These would be via the strong or weak nuclear interactions. For neutral particles, such as photons and neutrons, we have what's called the photoelectric effect. Photon comes in and it produces an electron getting excited, excited out of its bound state within a nucleus. Then we have Compton scattering, where the photon just scatters off an electron, moves the electron at a high energy away from the nucleus. Electron-positron pair production. So this is photon comes in and produces an electron and a positron. Nuclear scattering and capture for neutrons and other nuclear interactions. For the neutrinos, which only interact via weak interaction, this becomes an indirect process. No matter what interaction type it is, though, we need to build detectors that can convert the signal into an electrical current that we can read and digitize. So that's usually done with a signal chain, an electronic signal chain. So in the picture here, you can see, for example, the detector on the left hand right here. The detector just gives a current signal. It's amplified to produce a larger signal. There's possibly a filter to filter out noise. There might be something like a cable driver that prepares the signal for transmission to another electronic component, which does more filtering and the digitization with the so-called analog to digital converter, which takes an analog signal and turns it into something a computer can process. So what type of different detectors do we have? We have scintillation detectors, for example. Here, the energy loss of the particles by ionization. The particle moves through a transparent material and ionizes the electrons, moves them from what's called the valence band, where the electrons are bound, into the conduction band, where they could be conducted. And then they decay back from this excited state, producing UV or visible light in a process called luminescence. This can be done with both organic and inorganic or crystalline transparent materials and substances, as well as gases. The light is emitted isotropically in all directions. And usually what you need in order to then see the signal is you need a conversion of the light to an electric current. So on the right-hand side here in the picture, you can see these pieces of equipment here, for example, a photodiode. I'll get back to what that does. But this converts the photon into an electrical current that we can then process electronically. So some applications of scintillators are they can be used as simple triggers. In other words, they can tell you whether or not there was an event or not. They are energy sensitive, so they can be used for calorimetry. They are very fast, depending on the type of detector, so they can be used for timing. They can be made very thin and they can be segmented, so they can be used for tracking. They can be used for energy measurements, time of flight energy measurements, for example, which is illustrated here. And they can be used for pulse shape discrimination as well, so for particle identification. The drawbacks are that they're sensitive to impurities and radiation damage. So then we have Cherenkov detectors, which is a coherent, fast form of radiation for super-relativistic particles. It works for charged particles that move through a certain medium. This process depends on the speed of the particle to be faster than the speed of light in that medium. If the particle is slower, then here C divided by index of refraction, then you have no Cherenkov radiation. And if the particle is faster than C, the speed of light divided by the index of refraction, then the particle can radiate photons, even if moving in a straight line, and that gives you Cherenkov radiation. The Cherenkov radiation is emitted at a specific angle that depends on the speed of light, the index of refraction of the material, and the speed of the particle moving through the material. What you can get as a result, if you build them, if the material, the active detector material is constructed properly, is total internal reflection. This is illustrated right here in this picture. The applications involve PID and background suppression. So, for example, particles below the threshold to make Cherenkov light don't make a signal at all. The threshold depends on the particle mass. So, for example, in this lower left-hand plot, you have the threshold momentum for a particle versus index of refraction. So for example, electrons are way down here, so they don't need a lot of momentum to make a signal. But then if you wanted to reject, say, pions, protons or kaons, which are other types of particles, then you would pick a material that allows you to do that with a given index of refraction. So some examples. So this, for example, would work for a very low index of refraction material, such as an aerogel detector, which is shown right here on the right. Quartz is another material that you can use as a Cherenkov detector. It rejects soft photons, so X-ray and gamma ray background. For ultra pure quartz, it provides low scintillation. So again, there's background rejection. And you can collect as much light as possible by total internal reflection. And then here are some examples of detectors that our group has been working on over the years, exploiting that technology. An example of how this is used, for example, in neutrino detection is in two large-scale detectors. Here on the upper right is shown the Super Kamiokande detector in Japan, which detects neutrinos by conversion to electrons, and the electrons move through water, and water acts as a Cherenkov material, and they produce these forward-going Cherenkov cones that you can then see in your events. And you can distinguish electrons and muons, for example, by the shape of their rings. The Sudbury Neutrino Observatory in Ontario uses the same technique to detect neutrinos as well. You need photosensitive devices in order to convert the light that you see, either from scintillation or Cherenkov, to an electric current. So you use the photoelectric effect to do that. So the photon would come in here from the left, it would hit a photocathode, emit an electron by a photoelectric effect, and then that electron is accelerated by a potential to what's called a dynode, another cathode type material that when the electron hits it, it emits more electrons. Then those electrons are again accelerated to another surface which emit more electrons, and so on and so forth. So you get what's called an electron avalanche, which at the anode at the end leads to a detectable and measurable current that you. A similar method for lower energy particles are called microchannel plates. So here you have these many individual channels right here that are all covered with this cathode material. So you might have an incoming particle here that basically hits the one channel, makes two electrons, then those electrons make more. And again, there is an electron avalanche that produces a large detectable current at the output. So here at the University of Manitoba, for example, we've been building these 15 by 15 centimeter squared multi-channel plate detectors used in order to detect low energy protons. They are currently the largest multi-channel plate detectors in the world. Then you have gas detectors, where you have a container that's filled with gas, and you have particles moving through the gas, and they ionize the gas, and then you apply fields. So, for example, you have high voltage plates right here, and then you have wires here at these dark points that serve as anode wires. And you produce these large fields that then collect the ionized charges. So here's, for example, an electron path moving through the gas. As it moves through, it creates electron-ion pairs, and the electrons and ions are guided to these wires by the field. And then you can detect the current on the wires. So these are very useful for tracking. They can be made so that the signal is very highly amplified at the wires. So even from a small signal, you can get a very large, from a small individual event, you can get a very large current signal. They can be highly segmented, so they can be used for precise tracking. Depending on the gas, they can be used to detect also neutral particles. And they allow for good photon background rejection, and they can be made thin, which is good for tracking. Thin here in quotation marks means they might be, as far as the volume is concerned, they might be large, but the fact that you use gases means that they don't really distract the path of the particle moving through, which is important for tracking. And so that's what we mean by thin. And they cover large volumes and areas. An example here is, for example, a large cubic drift chamber that was built for the aforementioned cubic experiment, which was 3 feet by 8 feet with crossed wires like this. What you can do, and then here's another picture of them installed in the experiment. So you have 1, 2 multi-layer wire chambers, and what you can do with them is when you have a particle path moving through them, then from each of the wire planes in each of the chambers, you get a track pattern, and you fit a line to it, and that allows you to extract the exact path of the particle. Another example here, for example, is one that we built here at the University of Manitoba, which was used in order to detect neutrons, cold neutrons that enter this wire chamber right here. They capture on helium-3 gas that was inside this chamber. And what happens after the capture is you get the excited helium-4 nucleus decaying into a proton and a triton. And they are both charged and they move through the gas and they deposit their energy, which is this curve right here. And then as they deposit the energy, they ionize the gas and you pick up the charge or the current from the ionization on these wires inside the chamber. Finally, the last set of detectors that I want to introduce to you today are called semiconductor detectors, probably the most high-tech form of detectors we have now. They're used for photon spectroscopy. They can be used for vertex detection because they are very precise. They can be used for energy measurements of charged particles that are low energy. They use microchip technology to make, which allows for very small device structures and small spatial resolution. So they are highly pixelated, and the pixels can be made as small as 10 micrometers now. If you make large volumes of them, they can be relatively low cost, and they require very low energy deposition for detection. The drawbacks are that they have a high design overhead, so you need, in the design process, they're very complicated to design. And normally they have low radiation damage tolerance, so they break easily in high energy experiments, except for a few special type of detectors that we So the basic functionality is that electrons, the particle, not necessarily just electrons, but any type of particle moves through the detector and excites electrons from what's called the valence band to the conduction band. So this process is shown here. Then you can apply a potential and lead off the current. So that's illustrated right here in this picture. You can dope these materials. So for example, you can dope silicon with impurities, which increases the number of charge carriers, so holes or electrons, creating so-called N-type or P-type materials. And this level of doping basically determines how easy it is to create free charge carriers. In other words, to move them from the valence band to the electron band, to the conduction band. When you form a junction between N-type and P-type materials, they form a basic semiconductor diode. And biasing these diodes will then allow the collection of charges and reading a current signal when a particle passes through these type of detectors. So this is a very basic type of silicon detector. Some examples of that are your standard CCD, so basically what's in your digital camera in your phone, although the newer ones are slightly different. Those consist of many diodes arranged in highly segmented pixel arrays. So this is a one used for observational astronomy right here, a high-resolution, highly pixelated CCD. You can combine those with special dyes and other types of filters that can then distinguish between red, green, and blue photons. They're used in many scientific applications, from medical imaging to observational astronomy. And then we have so-called surface barrier detectors. There's one example shown here that we're using in one of my experiments. It's called a fully depleted semiconductor layer that allows for energy deposition measurements of particles. It has thin entrance dead layers allowing for measurements of very low energy particles, in our case, protons from neutron beta decay. And there are the more sophisticated, more modern type of silicon detectors that use the CMOS technology, which basically means that P-type and N-type diodes are implemented in, and transistors are implemented in a single pixel. So you don't just have these individual pixels, these individual diodes anymore. You now have electronics implemented in every pixel. So the electronics consist of amplifiers, discriminators, analog to digital converters, and so on and so forth. And they can be built right into a tiny little pixel, sort of 20 by 20 microns. The detectors can be made extremely thin, sort of 50 micrometers thin. And that makes them very resistant to radiation damage. The thinner the material and the smaller the structures, the more radiation hard these become. So they have been measured up to 300 megarad, and LHC detectors claim 1,000, that they want to get to 1,000 megarads. So these types of electron detectors are proposed for use at beam polarimetry at Jefferson Lab and other facilities. That's one of our projects. And some of these detectors, many of these detectors are, for example, built into central trackers in these high energy collider experiments. So thank you very much, and I apologize for going a little over time. So here I just finished with the slide that shows the current active members of our group, faculty members of our group, subatomic physics group at the University of Manitoba, and some of the facilities that we currently do. Thank you very much.
All right. Thank you so much, Michael. If we can put the screen back to the questions. For those of you who have questions, please go to slido.com and enter 6307. So I'll be moderating those questions. We have a couple of questions for you, Michael. The first one is, can you tell us about applications of these detectors outside of physics?
Yeah, I mean, in very general, broad terms. So let me see.
You mentioned CCTs in one of your slides, but if you can elaborate on other types of applications.
So in very broad terms, a lot of these silicon detectors, in particular, used in medical imaging applications, for example. They're used, of course, in radiation monitoring and particle monitoring in many applications outside of physics directly. But one thing that comes to mind is medical diagnostics and imaging, for example. So that's particularly true for these CMOS detectors that are very popular or becoming very popular in high resolution imaging in medical.
Okay, great, thank you. The other question is, do you have any new types of detectors? Do you have any ideas for new types of detectors?
Well, usually, I mean, the things that I've mentioned in this talk refer to the basic technology that you can use in order to detect particles. There's many variants of these detectors, and the innovation usually comes in how you combine these different technologies to build bigger detectors. For example, one new way, for example, would be if you take, in this particular slide, if you take these semiconductors, and this is something that people are already thinking of too, and you were to code them with a type of material that allows UV, for example, it allows them to become UV sensitive. Then, as an example, let me go back here. Now, what's often used are these photomultiplier tubes in order to detect the light from, say, a Cherenkov detector or scintillation detector. What you could use with a detector like that is these CMOS semiconductor detectors. If you treat them, surface treat them, they can become very sensitive to UV. And you could attach them to these scintillators or Cherenkov detectors directly rather than going through a photomultiplier tube. It would make construction of some of these large detectors very easy, or not very easy, but much easier than it is right now with photomultiplier tubes. And then you can possibly use these type of detectors also outside of physics by modifying them, packaging them, and maybe combining them with certain biological substances. And people are already doing that as well.
All right. The next question is, you mentioned that Cherenkov detectors was only able to detect a certain particle if it was faster than the speed of light. How is that possible?
So it's not faster than the speed of light in vacuum, right? So we have the important distinction here is that nothing is faster than the speed of light in vacuum. But in a given material with an index of refraction different than that from a vacuum, you can have particles that move through that material faster than light would through that same material. And so, if you accelerate particles high enough, and I've shown some numbers here. For example, for these particles right here, so for example, the 12 GeV electron is so close to the speed of light in vacuum. C is always the speed of light in vacuum. But inside another medium, such as quartz, for example, the speed of light is slower than this particle moving through the medium. And so in that case, and only in those cases, the particles for which that is true can radiate energy, which is called radiation, which you see in form of light. Depending on the material, that can be in the UV or slightly.
All right. A question from Janet. Can you elaborate more on the QWEEK experiment? Is there any research on QWEEK at the U of M?
Yes. So let me, right here. So let me go back to this slide right here. So the QWEEK experiment was a large experiment that started construction in development and construction in the early 2000s, and published its final result actually in 2018. What this experiment did was it scattered high energy electrons off of protons. So here the sample would be a proton, scattered the electrons off of the proton, and then detected the number of scattered electrons here in the detector. And they did this as a function of what's called helicity, or the spin state of the incoming electron. And it allowed us to study what's called the weak charge of the proton. So the proton, of course, has an electric charge associated with it, But what that really is a number that sets the strength with which the proton interacts electromagnetically with other particles. But there's also this thing called the weak interaction, which is the main driver of energy generation in stars, for example, the underlying process for that. And the weak interaction also has a strength. So the proton is also a particle that interacts weakly with other particles or via the weak interaction. And so it has a so-called weak charge. It's not really a charge, but it's just another number that sets the strength of that interaction. And so we wanted to measure that to very high precision. And the detectors that you see here on the very right, these detectors right here, were constructed to a large extent by the University of Manitoba group and people from the University of Manitoba. People that are now in our group were involved in building these tracking detectors over here and making the collimator and the spectrometer design, studying the optics of the experiment. So this whole experiment over many, many years had a large involvement of the Manitoba group.
All right, so we're running out of time, but I'll ask a couple of questions, and please, if you can answer them very briefly. A question from Kyle. What physics ideas would be a detector, and what creative ways can we come up with if we do reach the limit?
I'm sorry, you were breaking up there. I didn't get the beginning of the question.
So the question is from Kyle. What physics ideas would limit a detector, and what creative ways can we come up with if we do reach the limit?
If I understand the if I understand the question correctly, he's asking what what limits do we reach with the current detectors?
Yes.
Okay, so so I think the limits are not on the detectors currently. I think in terms of high energy physics, the limits are clearly on the energies we can reach with a given accelerator. So they're more on this side than they are on this side right here. So I think as far as detectors are concerned, there's still a lot of headroom for being creative with the technologies that we have so far. But certainly these new semiconductor detectors that people are now developing are a major step forward.
All right, great. So 2 questions, I'll cluster them together. What are some of the biggest concerns for you when building a detector in your work? And are silicon detectors something we can build in the labs at your lab?
Personally, for me, my biggest concerns are always noise. In detectors, there's always noise and unwanted backgrounds. And then the next biggest concern currently in an experiment that I'm working on is radiation damage. These experiments produce so much radiation, radiation levels that are found nowhere else on this planet, that it's easy to destroy things if you pick the wrong material. So that's a major concern. And then you want them to be low noise and high precision. So my biggest concerns are always, how well can I build the detectors and how well can I build the electronics to make them high precision detectors. And so silicon detectors is something up to a certain size or structure size we can do here. In terms of designing, we can do a lot of things here. And there are some people here at the University of Manitoba that know a lot about designing these sort of things. And then usually we use services such as CMS that are provided to us in order to have access to foundries that may make prototype chips. If you really want to make them for the final version, you have to go to larger foundries and you have to participate in what are called microchip engineering runs. And then usually what that takes is either a large volume or getting together with other experiments in order to finance it.
All right, great. We're running out of time, so if you have any question that did not get answered, feel free to contact Michael directly. I guess his email address is his first dot his last name, michael.gericke@humanitoba.ca. So thank you everyone for all your great questions. Thank you, Michael, for this great talk and teaching us about the physics of detectors and the amazing work being done at the University of Manitoba. So the next talk will be by a mathematician, originally a mathematician, who got his degree from science here from UManitoba and currently a well-known economist, Dr. Hirsch Sheffrin, who's a professor of finance at the Levy School of Business in California. So I hope we'll see many of you and more next week. And I should remind everyone that the talks, subject to permission from the speakers, the talks will be posted for later viewing on the University Faculty of Science YouTube channel. So make sure you follow us and watch anything you might have missed in previous weeks or you might miss in the coming weeks. So I look forward to seeing you again next week. And until then, please do take care. Thank you, Michael, once again, and have a great weekend, everyone.
Thank you.
Bye for now.